Excellent, fantastic. I'm Ben, I'm from MPI-A in Heidelberg. I'm supervised by Karim and Hans Walter, and I'll be talking to you guys about Gaia astrometry and what we can use with the wealth of information that Gaia has for binaries to constrain the populations of binaries and their binary parameters. I think it should be obvious that Gaia is useful for many different kinds of binaries. Of course, its third data release, 34 months of data, provides information on many different kinds of binaries, and probably the most obvious case is the NSS catalog, where we have these 168,000 full orbit solutions. But of course, most binaries are not in this catalog, right? Consider what might be the conventional wisdom for the period distribution of binaries. For things that are maybe like the sun, you have some log normal distribution, maybe peaks at about 10 to the 5 days. And the orbit solutions we have in Gaia are only going to go out to 10 to the 3 days, maybe. Meaning that most of the objects hanging out over here are going to look like single stars in astrometry. And so, if we want to have some comments on the statistics of the binary properties for the whole sample of binaries, we need to have some machinery to look at the information for everything that even looks like a single star. When I was planning the talk, Hans Walter told me, this is how you should start the talk. You should say, imagine you have all this information, and why the hell is nobody using it? I guess his solution to that is to import a Canadian to have a look. And this all comes down to the basic idea of, well, I want to learn something, right? So I'll have some data, and then I will learn something by envisioning some parameterized model. And I will learn that by saying, well, what is the most likely set of parameters given that data? If you're a Bayesian, and I normally am, what you do is you calculate the likelihoods, you go the other way around. Talk more about that in a second, but for now, I'll go through the data that Gaia has for us. So for 1.5 billion objects, Gaia fits a single star model which has 5 parameters. I hope the writing's big enough. If something's not clear, just yell at me. I'll fix it. The 5 parameters, you get a parallax, the positions on sky, and their proper motions on sky. And then Gaia will see how good this fit is, and you get a renormalized unit weight error. If you're German, you call that Ruve, and I will. If Ruve is greater than 1.4, the historical cut, then this thing is probably a binary. And then there's a different set of solutions that Gaia will try. There'll be a 7-parameter solution, where you'll get these 5 parameters plus the on-sky accelerations. There's a 9-parameter solution, where you'll get these 5 plus the on-sky accelerations, plus the jerks, or the derivatives of the accelerations on sky. And then, of course, you have the things with 12 parameters, full orbit solutions. You get the orbital angles and all that. And that's all well and good, but it's not clear a priori how the distribution of these different solution types will depend on the binary parameters. Of course, to do that, we need to compute this thing. This thing, envisioning some model, and then what data your telescope would get with that model. That's just a forward model, right? So what we need is to forward model Gaia. Fortunately, we have this, Gaia mock, written by Karim. Gaia mock will use the uncertainties of scanning law observing cadence in Gaia, will tell you the astrometry that Gaia probably would have seen, compute the Ruve, and then assign it a solution type. Of course, if I want to get some data for a given binary, I need to tell Gaia mock everything about that binary. A period, the eccentricity, the masses of the 2 objects, the parallax, the flux ratio, the apparent magnitude, the positions on sky, and the proper motions on sky. Oh. And of course, the orbital angles, which there are 4 of. Okay, that's about 15 parameters. And really what it comes down to when I say I'm learning something by computing a likelihood, I'm going to create some objective scalar function, run a Markov chain, get a posterior. Excellent. Well, if I want to do that, I want to be able to compute this thing really, really fast. Maybe I would like to pre-compute every possible binary's data and then look it up later at the time of inference. Well, if I have 15 parameters, that's a bit impractical. Fortunately, most of these things I don't care about. Positions on sky, proper motions, orbital angles, I do not care about these things, and I can marginalize over them. I have good understanding of the distribution of these things, and so that will just blur the distribution of the data that Gaia mock gives me. All right. If I live in a world where all of my companions and my binaries are invisible, flux ratio is 0, so we can ignore that one. And even if you don't make that assumption, it's still fine, because if you have some mass luminosity relation, then the flux ratio will just be tied into the mass ratio. So we don't need that separately on its own. And if we have a narrow range of apparent magnitudes, apparent magnitude won't make a big difference. That's nice. We still have 5 parameters. We could still do better than this, right? Because the period is obviously very important, so is eccentricity. If you have a period way longer than the baseline of Gaia, you're not going to be able to constrain an orbit. But imagine we hold a period constant, and we have some star orbiting a black hole, and its orbit looks like this on the sky. Then I take it, and I move it further away. What happens? The orbit looks smaller. What if I take this thing, hold the period constant, and decrease the size of one of the masses? What happens? The orbit looks smaller. Meaning that I have 2 orbits that are fundamentally different, but to Gaia they would have looked the same. So I don't need to compute them each on their own. I can compute it once and then look it up a second time. So really, between the 2 masses and the parallax, there's only 1 degree of freedom. So all I need to get the distribution of some data for what Gaia would have seen for an object, I just need to ask GaiaMock what that would be for just 3 parameters. This is really excellent because with 3 parameters, I can reasonably go and just compute it for every possible binary. And so this is what you can get. Imagine a binary that is, let's say, a circular orbit. The primary is something like the sun, and it'll be sitting something like a kiloparsec away. And then I want to ask for every possible mass ratio. That is the ratio of the secondary to the primary. And then for every period, what is the most likely solution that I would have got? And it looks something like this. Over here, you'll get orbit solutions, peaking about 10 to the 3 days. You have this little gap at about a year, because it's degenerate with the parallax. Then sitting just above this, you'll get the jerk solutions. Above that, acceleration solutions. And then vaguely something like this, you will get a high Rouvet. And over here, you'll get a low Rouvet. First thing that jumps out is it's pretty horizontal, meaning that the type of solution you get is very dependent on the period. Also, if I were to move the object further away, this plot would kind of just shift to the side. You would need to have a higher mass ratio to get the same solution type. If I were to increase the eccentricity, this plot will kind of just blur vertically. So the simple fact that we have different solution types given to different objects is actually quite powerful, because it will, just looking at this, tell us about the period distribution. The eccentricity distribution, of course, it's implicitly dependent on the mass ratio distribution. And if you assume that your single stars can't get a high Rouvet or end up here, and you have some global period distribution, you also get the binary fraction. So this leaves many different routes of inquiry. For example, the binarity of different populations, or looking at the distribution of binary properties for different populations. For the case where we have the invisible companions, it's the same if you want to look for black holes or for brown dwarfs and planets. And DR4, I think this is only going to become more important. We have a few dormant black holes right now, but if we have, let's say, a couple dozen or something in DR4, this is a type of machinery that you will need to use to make meaningful constraints on their properties. That's all I have. Thank you very much.
By the way, all the other talks in the session will be on the blackboard, too.
Thank you. A very novel talk. Thank you very much. Were you talking about the left region? Were you ignoring the possibility of singles?
What do you mean?
You were saying that you would have data when the period is fairly short.
Yes.
When the period is long, you may not be able to say that there's an association.
Yeah.
But is that the case? Are you looking at the left-hand side only with this analysis?
No. I could add in here, for example, the acceleration solutions go out to a bit higher, and then high Rouvet goes out to a bit higher periods. So you aren't necessarily probing out to 10 to the 7 days, But the fact that you have some number of objects with a low Rouvet is going to place constraints on your period distribution because you're going to need a certain number of objects there.
I guess my perception is rather primitive.
Yeah.
If they're fairly separate and at large period, can you look for a common proper motion? Or where in this analysis is the
yes.
search for common proper motion?
Yeah, so when you do this stuff with the astrometry, there's two populations that you lose. When you're down here, you have the stuff that's really close by circularized.
Right.
Then when you're way out here, roughly 10 to the 8 further, then you're going to have the resolved stuff if it's close enough by. And so if I constrain some binary fraction, well, that's not accounting for these two different populations. So yes, the resolved stuff you won't really see. You kind of have to ignore those.
Okay, I have a few more questions, but maybe.
Okay, we'll talk after.
Cool talk. I guess, how are you handling this framework things that have a large RUI for other reasons? Like astrometric microlensing or just like a bright star contaminating it or something like that?
Yeah, this is of course a problem if you're going to have something wrong with the measurement or like a triple or something. The simple cop-out answer is that I'm doing some Bayesian stuff and I can throw a term at the end for my outliers. Otherwise, you can hope that, for example, in these things, the contamination won't be too high.
Can you speculate on how other kinds of information, like radial velocities that Gaia is also measuring, will inform what you're doing at, or at what period range is relevant?
Yeah, that's excellent. This is something I've been thinking about because another thing you could in principle do with this is take an individual object and try and constrain its properties. So if I have some object and it has an acceleration solution, it probably lives up here. If I have its Rouvet, for example, that has a slightly different distribution, but I don't have a good constraint on the mass ratio. And so getting the other axis, rate of velocity, something of that variety, helps place a constraint on the mass ratio, but of course, only in a low enough period regime. Yes. And that would be really what I'd like to do going forward is connect this with other data that Gaia has available or other telescopes, et cetera. Place better constraints.
So you said you could ignore the flux ratios, which I don't quite understand, or that you assume, that you now have a mass luminosity relation. Which do you actually do? Because I think that makes a big difference in the astrometry.
Yes, it makes a huge difference. So the stuff that I'm working on right now, I'm just have invisible companions, so I get to ignore that. But if you have some mass luminosity relation, then what happens is the flux ratio is related to the mass ratio. And what you follow with Gaia is not the two stars, but the photocenter. And the photocenter moves predictably with that flux ratio, which just depends then on the mass ratio if you have some global mass luminosity relation. And so this doesn't change at all, just this formula gets an additional term. Or an additional thing that you multiply it by, and that's about it. If you are happy with the mass luminosity relation, that is like some power law or something.
Except there's not. It's not one mass luminosity that you use.
Sure, if you have a sample where you have one type of star where you can impose such a thing, yeah.
All right. Could the next speaker come and start setting up, and we'll take one more question?
Just Jessica wanted to make a comment on the luminosity ratio business, which is a big deal indeed. I think in practice, Gaia has these beautiful SCDs from the XP spectra. That's a way to get a handle on this. It'll hopefully also have the RVS spectra. You can look for SB2ness of any sort. And one of the things we've actually done in SDSS5 is, Karim's idea, any astrometric binary, we take in a single epoch apogee spectrum to just look where there's SB2ness. I think that's right. There are various ways of trying to pin this down.